Welcome to another video in the Matrix of Time series. In this one we're going to be dealing with quantum spin. So let's tuck right in. So it's kind of a repeat here. In a previous series we talked about a universe in constant motion, but in actual fact it's a universe in constant rotation. So the sun is spinning, the earth is spinning around its axis, it's spinning around the sun, the solar system is spinning around the Milky Way galaxy, all the stars are spinning. The whole universe is in a constant state of rotation. In this slide we'll talk about all the types of spin that can happen in the atomic world. And the first one shown here is orbital spin. And that's where the electron or electrons spinning around the nucleus set up a spin orbital momentum, and this accounts for a lot of the magnetic fields that we see in matter. The next one, and in this case we'll see another electron shown much larger so that we can show the types of spin in more detail. The first one is where the electron spins around its axis, and we'll call this axial spin, and this is the quantum property of spin. And this spin creates a magnetic dipole. The magnetic dipole is where you have a north pole and a south pole. And magnetic poles always come in pairs. They're never seen as an independent north or an independent south pole, no matter how small you divide matter, unlike electrical charges, where you can have a positive electrical charge separated from a negative electrical charge. And those are called electrical monopoles versus a magnetic dipole. And so the spinning electron creates a magnetic field from this axial spin. And then if there's an external magnetic field to this atom, it'll interact with this magnetic field that's generated by the axial spin, and it'll cause the axis of this spin to tilt off angle, and that's called a precessional spin. And so it'll spin at a different rate than its axial spin. And then finally, depending how the external electromagnetic field is introduced to the atom, it can cause the electron or electrons to spin flip. So they'll spin. So instead of having a north pole pointing up, the north pole will be pointing down. And so that gives you a feeling for all the different types of spin that are possible in the atomic world. So spin and magnetism, this coupling of spin and magnetism is not only just seen in the atomic world, but we can see it in the spinning of the Earth. Anytime you have a spinning electrical charge or a body that has an electrical charge, like the Earth or the Sun, that is spinning, it will generate a magnetic field. And we see that with the Earth, the magnetic field is generated by the spinning of the Earth. And in actuality, the orientation of this magnetic field of the Earth will flip with no regularity. And for the Sun, the same thing. It has a magnetic field with an orientation, and the Sun flips its magnetic field orientation pretty regularly every 11 years. So we go from a solar maximum to solar minimum, back to a solar maximum on an 11-year cycle. Now, let's get back to quantum spin. This is where the interesting things really happen. So we have on the left-hand side where we see a typical particle, and we talked about the axial spin, the precessional spin, and the spin flips, and that happens when we're observing it. But what happens when we're not observing it? So this electron doesn't behave as a particle anymore. It behaves as a distributed waveform. So it's distributed right through space. So then the question is, well, what is spinning? So quantum spin is a property that atomic particles have as if they were spinning. Nobody really believes that they are spinning. It's just easier to think that way, and they behave as if they are spinning. So the magnets that we're so familiar with and all the magnetic properties of matter are based on this as if it were spinning property. So that's kind of a puzzle. So quantized spin. So just like energy is quantized, so spin is quantized. It can only come in packets of h over 2, and remember h is Planck's constant. So typically in quantum theory, for spin the h is ignored and it's just stated as a half. So think of, let's go back to rotational velocity. So when we see a top spinning, we rotate just about anything. We know that we can rotate it faster, slower. You think about the tires on a car. There's no limitation to how precise we can get them spinning. But once you get into the quantum world, they can only spin in increments. So in other words, that tire could only spin a certain amount when you're going 5 miles per hour, and then the next would be 10 miles per hour, 15 miles per hour, and 20 miles per hour, but it could never spin at 18 miles per hour or 7 miles per hour. That would be unallowed. And when we look at the spin of these atomic particles, we find that the spin is measured in plus a half, minus a half, plus 1, plus 2. So those are the common amounts of spin that are allowable in the quantized world. Now let's go back and look at the graph on the top right, and we can see that each one of those jumps is h, the amount of Planck's constant. And how much is h? Well, h is a very small amount of energy. And to give you an insight, if you turned on your smartphone flashlight for 1 second, then h is a little bit less than a billion million times smaller than the energy of that light in 1 second. So it is quite small, but it's all relative. And from our perspective, that's an extremely small amount of energy. But from the quantum world, that small amount of energy can have significant effects on the properties of the atomic world. So in order to go forward and understand how spin fits into the quantum world a little bit better, let's just talk about quantum states and quantum numbers. Now, each quantum state is made up of 4 quantum numbers. The first one is the principal quantum number, and that's basically related to the electron shell. Now, when we visualize all of these states, we're talking about visualizing the atom in the particle state. So we visualize a nucleus as an object, and we visualize all these electrons as particles, because if we try to do it in the non-local or distributed form, it just doesn't work in our imagination and our understanding. So we'll stick with the particle form. So the principal quantum number is these electron shells. So you have the inner shell and then all the outer shells that get filled up with these electrons. The graphic shows 2 combs, and basically each comb would represent the principal quantum number. The next one is the orbital quantum number. And if you remember back from a previous couple of slides, that we talked about the orbital quantum momentum being the amount of energy that was generated by the electron spinning around the nucleus. The next one is called the magnetic quantum number, and that is some energy level splitting that happens when you put the atom into an external magnetic field. It's called the Zeeman effect, but basically, if you look on the right-hand side, the teeth of the comb represent the finer structure, which is the orbital quantum number, the magnetic quantum number, and the spin quantum number. So depending what values these are, these create finer structures of the energy levels. And so the 4th quantum number is related to spin. And what you notice is that quantum number 2, 3, and 4 are approximately h. It's nominally n, and n can be 0, 1, 2, 3, 4, 5. But you can see that it's small integer values multiplied by h. And as you learned before, h is a very small number. So it splits these energy levels into fine structures. And we're not going to go into the other ones because this whole discussion is about spin. But what I want you to remember is that as we talk about spin, and we talk about spin being plus a half or plus 1, we're talking about basically h divided by 2 or h multiplied by 1. So half and h are constant. And as you saw, it's a tiny amount of energy, but it has dramatic effects. So let's look into the classifications of spin. Now, quantum physics divides up this spin into two classes. The first class is called fermions, and those are atomic particles that have a spin value of a half, so plus a half, minus a half. The second class is called bosons, and those have spin of integer value, so plus 1, plus 2. And you might say, what's the big deal? So let's go through this example. So if you're going at a speed of a half, granted it's rotational velocity, but think of something spinning, and it's spinning around at a speed of a half, then the quantum rules say that you're limited to just one fermion with a unique value of spin. And remember, fermions can have plus half or minus a half. So that means that the most fermions that they could be in a quantum state would be two fermions paired up, one with plus half and one with minus a half spin. So in this example, I'm going to try and use vehicles to kind of explain the difference between fermions and bosons. The goal is to give you an appreciation for why spin is so unusual. So let's take a vehicle and we'll say that these vehicles represent allowable spins in each quantum state. So on the left-hand side, we have cars, and on the right-hand side, we also have a car. And we'll just look at the aspect of spin. So the previous example said that each quantum state could only have one value for spin, so that, it becomes unique. So in the first example, we have people represented as spin up and spin down particles. So in this case, we have two spin up people that are passengers. So we assume that all of the people here are passengers and they're in the front seat and the back seat, and we're going to use these quantum rules to find out what is allowable and not allowable. So the quantum rules are that you can never have two people as passengers in the front seat, and you can never have two people as passengers in the back seat. You can only have a passenger in the front seat that's spin up and a passenger in the back seat that is spin down. Those are the only allowable states. And since the electron only has two spin states, then it moves to a completely different quantum state and it goes to a different car. So we saw in the first icon that we had two spin up, one in the front and one in the back. That's not allowable. We have in the middle a spin up person and a spin down, spin up in the front seat, a spin down in the back seat. That is allowable. Now, when a third person enters the picture as spin up, it's not allowed in that vehicle. It has to go into a separate vehicle, and there is some separation between all of these vehicles. So if the fourth particle comes in, if it's not a spin down particle, then it would be forced into a third vehicle. But if it is a spin down particle, then it would be allowed into the back seat of this car. So this is the case if these particles are fermions with spin half. But what happens if these particles have spin 1? Well, now it's in the right-hand side, and it's completely different. You can have as many spin 1 particles in the front seat of the car as you would like. You can have all of the people, if everybody on this planet, all 7.5 billion people were spin 1 people, they would all be allowed in the front seat of the car. And in fact, they could all fit in the front seat of the car. Now, in this example, I talk about spin as if it's something that you can just easily change. But really, it's nothing that you can change. It's something that is a static attribute of the particle. If you want to change the spin, you need to combine particles. So, for instance, you'd need to combine two particles with spin half to get a particle of spin 1, and you'd have to have a spin 1 particle break apart to create two particles with spin a half. But here in this example, I just want to give you the idea of how a very small amount of change in the spin changes the whole nature of the particle and its behavior and interaction with matter. And so you have this very unusual setup where if you're spinning at a rate of a half, you're forced into either being in the front seat if you're spin up and in the back seat if you're spin down. And if you have two particles that have the same spin up or spin down, they're forced into separate cars. And if you increase your spin to 1, you can have 7.5 billion people each sit in the front seat or the back seat. And if you slow down again to a spin a half, now all 7.5 billion people will be forced into separate cars, and they can only pair up based on whether there's spin up or spin down. And if you speed up again to spin 1, then everybody can be in the same seat. So you can see that this small change, and remember, the difference between these two is h divided by 2, and we saw that h is a tiny, tiny amount of energy. So even the small, tiny amount of change of energy in the spin creates radically different properties for the way these particles behave. Now, it's likely that this odd property of spin makes your head spin as it did mine. So this slide, I wanted to just summarize a couple of properties related to quantized spin that can be important in future series, where fermions are defined by half spin. And these are building blocks of matter. So electrons, protons, neutrons, neutrinos, those type of particles that make up matter, they have spin half. And they are forced to obey the Pauli exclusion principle. Basically, the Pauli exclusion principle helps explain how electrons combine in atoms to create the elements in the periodic table. You saw this principle in action when in the previous slide we talked about the aspect where only a spin up particle and a spin down particle is allowed in each electron orbital. And the example was that it would be a spin up person in the front seat and a spin down person in the back seat of a car. That's Pauli's exclusion principle, and you can see that the result was that a third electron comes in, it's forced into another car, there's a big separation between these, and so you can see how the Pauli exclusion principle builds up the electron configuration and creates a lot of space in matter. And spin is one of these quantum numbers that helps to define the uniqueness for each fermion quantum state. We could categorize these categorize fermions as having antisocial properties. When you look at bosons, bosons are ones that have n times 1 spin values, and these are the light and atomic particles that transmit fields. So the photons, the gravitons, etc. And there's no limit as to how many can occupy a given state. And these can be categorized as having social properties because basically the whole idea is that they can congregate billions of them together in the same quantum state. So one more puzzle related to quantum spin, and that's the amount of rotation it takes to come back to the same state. And we're going to use a card. Here is an example of Queen of Hearts to kind of help you to visualize what this means. So how much must a particle rotate to get back to the same initial state? So a particle whose spin equals 1 requires a 360-degree rotation to return to its initial state, and that's sort of as we would expect. So if we think of this card on the left where the two queens are not identical, so it needs to rotate a full circle. Now, a particle whose spin is equal to 2 requires only 180 degrees rotation to return to its initial state. And in terms of the card, where a 0 and 180 degrees would give the same result because both queens are identical. So if you flipped it 180 degrees, nobody would be able to tell the difference between 0 and 180 degrees. Now, what happens when we get to a particle whose spin is equal to a half? In this case, it requires 720 degrees rotation to return to its initial state. So you have to rotate it twice. And that's really counterintuitive. And the way to understand this better is in this card example. If you have to do this to simulate this 722 degrees, what you do is you place the card on your hand, palm up, and rotate it without dropping your palm. After 360 degrees, you'll find that your arm to be pretty contorted, but after 720 degrees of rotation, your arm has regained its initial position. And I've tried this myself, and it helps to at least visualize the 720 degrees, but nobody fully understands why the particle has to rotate, the fermion has to rotate 720 degrees to get back to its initial state. And the last property we'll talk about relating to spin is entanglement. The whole concept that we talked about previously of entanglement, it's all based on spin. So quantum theory says that if you generate twin photons, that spin is conserved. And what does it mean that spin is conserved? Well, it basically means if we assign plus a half to the spin up photon and minus a half to the spin down, then the total of these must always equal 0. So you can see that if you have the spin up turns down to spin down, then it would be minus a half plus minus a half would give you -1, and that's not allowed. So the whole basis of this entanglement attribute of the atomic world is based on spin, this conservation of spin that resulted from quantum theory. And the mind-blowing part about this is that it'll be true always. As we learned before, even if you have billions of miles between these, if one is changed from spin up to spin down, the other one instantaneously changes from spin down to spin up. So here we have another property where this property of spin is independent of distance between them. And again, this as if it is spinning property of atomic matter really defies our understanding. Takeaway messages. Spin of atomic particles is a property of matter that manifests as if the atomic particle is spinning. It's easy to imagine this when it's in the observed or particle form, but difficult to imagine what is spinning in the unobserved or non-local form. Atomic particles that are classified as fermions, where spin is equal to a half, have very different properties to bosons, where the spin has an integer value, spin equal to 1 or 2. Atomic particles require different amounts of rotation to get back to their initial state, based on the amount of spin they have. Fermions require 720 degrees. Spin is the basis for entanglement attribute that defies distance and time. In the next video, the different interpretations of quantum reality will be discussed. The behavior of the atomic or quantum world is unlike anything we imagined or could imagine. The last few videos on quantum theory anomalies have described a reality that challenges our understanding. So what has physics to say about this unusual reality of the atomic world? I hope you join me. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you will see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.